pull you inside. That's pretty awesome.
All right, electricity. Movement of those electrons. Now, if we don't have any electrons at all, would it? You think it would flow electricity very well?
No.
No, we'd call that an insulator. Insulator. Rubber doesn't have any of those electrons moving, so it's a really good insulator. However, copper, you also, you guys worked with copper yet?
Yeah.
Okay.
We touched it.
Okay, good. Well, whatever you do, don't make this mad. Never insult it, never be mean to it, because once you're mean to a copper, they never let that go.
He's back.
So the copper has a free electron on it, so it conducts electricity very well. Rubber doesn't have any of those free electrons, so it doesn't conduct electricity very well at all. So that's why we use rubber as an insulator, and we use copper as a conductor, right? So you put a whole bunch of copper in a line, put electricity on it, becomes a conductor, and choo-choo. Okay, so things about electricity that we need to know. Electricity boils down to this simple equation right here. E divided by R equals I. E, and it's over R, so that means divide. E divided by R equals I. But wait, that's not all. If I take E and divide it by I will find R. But what if I wanted to know E? Let's cover E up. Anytime two letters are side by side, you know what that means in math? Multiplication. So if I take I divided by R, I will find E. Pretty neat, huh?
You mean I times R?
I times R equals E, and E divided by I equals R, and E divided by R equals I. How cool is that? This is electricity in its simplest form. It's the equation that explains it. So first, let's talk about E. E.
Gotta be both.
Oh, very good. E is also known as volts. In the real world, E is simply volts. So remember the guy's name. I think it was John Travolta. No, it's just Volta. Something Volta. I think he was a vampire. Volta. But volts. Volts really means electrical pressure, or electrical push, or electrical force. Some people use electromotive pressure, electromotive force, but it stands for electrical pressure, electrical push or force, electrical force, pressure. Can you have water pressure in a pipe, but the water not be flowing?
Yes.
Yeah. Behind all your faucets, they're closed off and there's no flow, but there's pressure. So is there a potential for that water to flow?
Yeah.
Is it flowing?
No.
But there's a potential for it to flow. So we call this also potential difference. It has a potential to flow, but it doesn't have to actually be flowing. Potential difference. So when the guy came out with it, he called it E for electromotive or electrical. So he used the letter E. After he dies, I don't know if it's after he dies or not. It sounds good. It's usually what happens. After somebody dies, they're like, hey, we want to remember this guy because now that he's not here to be appreciated for it, we want to say, hey, how awesome that was. Anyway, so they started calling it volts after his name to honor him. And so we use the letter V for volts, even though it should be the letter E for electrical pressure. On the meter, I'm going to pass this meter around. You guys can take a gander at it. Over here it has the letter V for volts. Yep. Not vendetta. Right here, the letter volts, and the very bottom number is going to be reading, where it says V, that's going to be reading volts. And the other thing we use with volts, before I pass this around, let me cover this real quick. When I'm checking volts, I'm going to need to use the leads, okay? So these right here. And what we do is I'll put them in the plug outlet. I check between 2 points, the plug outlets, on a car battery. Whatever I need to check, I use these 2 points right here. Okay? So I got a friend that's a salesman. He's always looking for these. I'm like, it's on your meter, dude. It's right there. He's in sales. It'll come. I'll just let you think on that one a little bit.
No, I think we all thought about it. We decided that's the one we're doing.
My friend in sales is always looking for leads.
Yeah, I was all like, oh.
Oh!
God.
There we go. So we're going to use the leads of the meter, the 2 wires in the meter. But if I take those meter leads and put one on one side of the plug outlet and one on the other side of the plug outlet, will I read electrical pressure?
Yes.
You guys know how much electrical pressure is at that plug outlet? About 110, 115, 120, 125, somewhere in that area. If I want to know for sure, what do I use? No. I use the meter right there. I set it for V, for volta, and I use the leads, one on one side and one on the other side. What if I took both leads and put it on the same side of the plug outlet?
Get nothing.
Get nothing. Does that mean there's no pressure there?
No.
No. It's just where you're checking it, there's no potential difference. On a car battery, if I take and put one side on positive and one side on negative, am I going to read a potential difference between those two?
Yes.
Yes, about 12 volts if it's running or so, depending on, some other factors. But if I take both sides and put them both in positive, what do you think it'll read?
No.
It'll read 0, because where I'm checking, there's no potential difference. Does that mean there's no voltage in that battery?
No.
No. You'll find out real quick, right? But if I use my meter between those 2 points, you would see a voltage difference. So it's volts, potential difference. We use the leads of the meter between 2 different points. Speaking, we'll circle back around. We'll circle back around to it. So, next thing we're going to talk about is R. Oh, before we go to R, let's go back to volts real quick. All right, so this is my electron. If I push on this electron right here in this table, if I'm pushing on this electron, is that where to go?
No.
No, what if I push more?
You're just compressing it.
That's right. There's nowhere for it to go, right? But no matter how hard I push, now if I push it, is there a push on that? Is there a force behind it? Right, that's voltage. So it doesn't have to actually be moving to have voltage. So now we're going to go to R. R is the resistance to electron flow. R is the resistance to electron flow. So on this table, okay, here's a table right here. And if I'm voltage, I'm putting pressure on this electron, and I'm pushing this electron, does it have anywhere to go?
No.
It doesn't have anywhere to go. What's the resistance of this electron? Give me some other name.
You're putting the force?
I'm forcing it. Yeah, I'm adding a lot of force. I'm adding more pressure, that's right. But what's the resistance to this ping pong ball, this electron, what's its resistance to flowing?
Unlimited. Matter.
Infinite.
Uh,
It has infinite resistance. No matter how hard I push, it won't flow. It has infinite resistance. I can add more voltage or just a little voltage. There is no way for it to flow. The resistance to this is infinite. Kind of cool, huh? We'll circle back around to that shortly. So, anybody know who came up with resistance?
Last name
George Simon Ohms. To electricity, he was the original ohmie.
Just hanging with my homies.
Ohms. Ohms. What's up, Ohms? He was a pirate. R. I just want you to remember that the letter R stands for ohms, which is resistance to electron flow. And he was so awesome that he had his own symbol. He wasn't even in a band, but he got to have his own symbols.
So like horseshoes.
Is an upside down horseshoe. Looks something like that ish. You know why that's an upside down horseshoe? You know what horseshoes the correct way is like this, right? You guys know why they're like that?
To catch the good luck.
To catch the good luck. That's right. Good. Nobody ever gets that in the cities. That's good. So we call it an upside down
I didn't grow
horseshoe.
up in the city.
It's actually the
I
obviously.
just ended up there.
Me too. So this is called the omega symbol. So you guys don't even have to go to the big fancy colleges and you get your own omega symbol, right? And you can add some other stuff on there, omega crappa pie or something like that. And we have one more letter we're going to work with, and it's the letter I over here. But you guys probably hear it as something else. Amps. Amps. Amps, amps, amps. Amps is the speed of electron flow. Amps is the speed of electron flow. How fast those electrons are flowing. The speed of electron flow. How fast those electrons are flowing. Right? How fast is electron flowing now?
0.
0. It's not moving.
Yep.
Even if I put force behind it,
It's not moving.
still not moving. Right? So, speed of electron flow.
25 mile an hour curveball.
How fast is it flowing now?
Different speeds.
Oops, that was supposed to be you.
Yeah, dude, dang. Oh, you didn't catch it.
Oh, you didn't catch
Oh,
it.
you didn't catch it. Oh, let me see where your ball goes. Then he just started shooting him.
Speed of electron flow.
Look, man, you lying, boy. You got 2 under your chair. You didn't catch that one. That's it.
There's probably some up under.
Oh, you dropped him behind
Some
you.
under there from when you dropped it.
I already gave you one.
That's what I'm talking
All right.
about, dude. I missed it.
So, everybody hold on to your electron. Speed of electron flow is amps. So how fast is your electron flowing right now?
0.
0. It's not flowing. Now, if you put some force behind it without resistance, or with very little resistance, because air is resistance, and you put some force behind it, then you can have flow, right?
Yep.
Some good card shifts. Now, I want you to take your electron and flow it to the bucket.
No. Yeah, see, that sounds all bad for me. Yeah, no, 5 of them. No.
Oh! Speed of electron flows. So now without anything stopping it, you put some force behind it and that electron flowed. So amps is really, if you think about it, it's just really a byproduct of the volts and the resistance. Do you agree?
Yeah.
Volts and the resistance. So amps, speed of electron flow. And there's another word we use with amps. Anybody ever been swimming at the beach?
Yeah.
All right, so what do they tell you to watch out for?
Plastic.
That's true. Today, these days, there's so much more to watch out for.
Crabs, jellyfish, sharks, snake
So- Not including animals or pollutants or... Yes, currents! Yes! Watch out for the rip currents. Let's forget that. Let's go to a river. Okay, so the river is flooded, and you don't want to get into the river because of the current will be too much. And the current is simply the flow of the water, right? You can also have current, which is the flow of air too, right? So you can also have current being electricity. So electricity, if you hear somebody talking about electricity referring to what's the current, they're also talking about amps. They're also talking about speed of electron flow. They're talking about all these things because we keep having to find new words for the same stuff.
Yeah.
So current also means amps, which also means speed of electron flow, which also means the letter I. You might know any electricians in here. 2 people know electricians. Good.
Everybody knows. We all know one.
So it's all good to have electrician. It's good to have an electrician to know an electrician, because if you want to know what's happening, always ask the electrician, because they know all about current. They like to stay current. Right? And why do you think they use the letter I? All right, so the guy's name is a French guy, something Ampere. So sometimes you'll see it called amperes. And it was a French, some blah, blah, blah. Ampere was his name. He had a patch, and he had one eye, so he always had to, always missed. He hung out with George Simon Ohms, right? He was cool because he had his own symbol, right? So they were doing some electrical experiments, and they were out camping while they did this. And they did these experiments, and when they find all this happening and did these experiments, they didn't have names for it back then. And so they had to come up with a name for it, and they did this while camping. The pirates were out there camping, and so what they did was like, man, we found this flow of these electrons, and it was really intense. Because they were camping, right? So I stands for intensity. Intensity.
Well, that answers the question I was going to ask.
What's that?
When I was in high school in auto shop, they told us that when it comes to electricity, it doesn't matter how many volts you have, it's the amps that kills you.
It is the amps that kills you.
I was going to ask if the volt is the pressure or the push or the force, how does amp have anything to do with it? But the word intensity kind of makes it.
Let's think of it this way. The electrical lines, the big lines, the big giant lines that are flowing outside. A bird can land on those, right?
Yeah.
Is the bird killed? No. Now, the bird's on that line, so the electrons are pushing through that bird, but there's nowhere for them to go. But that bird is energized, so he's got 15,000 volts on him. 15,000 volts of pressure. The bird's like, hey, nothing's wrong with me, we're good. Right? But now that bird looks over and sees on that pole, oh look, a bug. And now he goes and touches the metal. Well, now there's a path. Now there's a path. There will now be a flow of electrons. Now there's a flow of electrons, aka amps. Now the bird becomes toast. Right? Pop. So, and even when they're working these power lines, they'll take, because there's no potential difference if you're on that line. They'll take a helicopter and they put a rod from the helicopter onto that wire, and it energizes the entire helicopter. But there's no flow, there's nowhere for electricity to go, so it's all energized. And a guy gets down there onto that wire, and he's fully energized with that voltage. With however many tens of thousands, 100,000, how many volts it is, ridiculous amount of volts. And he's under it, he's fully energized. And he's fine unless he touches something else. If he touches something else, there's going to be a problem. Now there's a path, now the electrons will flow through him. It only takes half an amp through your heart to kill you.
What about if you grab his tool? That would kill him too.
His tool?
Yeah, if any of your tool.
The tool's energized also.
It means if you touch one wire and you touch another that's separate,
Yes.
then you complete the
Because
that tool is already connected to you, so it's also energized.
Yep. So if I was to get a helium balloon big enough to carry me, and I could float, and I go over here and touch my finger into one of those, only one of that socket, I'm going to be fine. I'm energized. I have a potential for electrons to flow. The voltage is here, but there's nowhere for it to go, so it won't hurt me. I can jump up, grab one of those power lines, and it's fine. But if I am touching anything or on a pole and touch that line, now there's going to be a path for electrons to flow. Now there will be a flow. But as long as you're not touching anything, the resistance to electron flow is infinite. Infinite. You have infinite resistance. So when that bird's on that power line, there's 10,000, 100,000, 15,000, however many volts there are, I don't even know. That bird's energized that voltage. But the resistance from that bird to anything else is infinite. It's impossible. There's no path. There's no way for it to flow. So if I put it in my formula, 15,000 divided by infinity, doesn't fit my calculator very well, but if I try to do that math, what would your amps end up being? None. 0 amps. There'd be zero flow. There'd be no flow. Right?
So if two birds touching, just go in a circle like.
Now, if a bird is on this power pole and a bird is on this power pole, and they go and touch, then they're going to fry. Because now there's a big pressure difference.
But if they're on the same one and they touch their...
Same one, they're fine. Yep. No problem.
That's why birds and feathers flock together.
So far, so good? So volts is electrical pressure. R is the resistance to electron flow. And amps is simply a result of my volts and my resistance. Now resistance, what we use in resistance is a lot of times is going to be our loads. So for example, you guys know what this is?
Toaster.
You put in it? Bread. You guys were going to say toast.
Called pizza.
You were hoping we'd say toast.
I was hoping you'd say toast. Right? So this is an electrical load. This has resistance. Okay, it has resistance to it. I can find out what that resistance is with my meter. So my meter, I'm going to set it to something. Oh my gosh, there's all these symbols and little letters on here. I wonder which one I should pick.
Ohms.
Like the ohms.
Like domes.
Oh, the upside down horseshoe. There we go. So I'm going to pick that one. And then what it's going to do is it has a battery in here. And the battery is going to send that electrical current through one of these wires. On the other wire, it's going to read how much it's getting back. So when I put it on here, I'm going to clamp it here, and I'm going to clamp it here. And now I have to close the switch here. And it's going to tell me the resistance of this toaster. The resistance is 15.3 ohms of resistance. Ohms of resistance. So if I wanted to do the math, I'd put in it right here, 15.3. If you're going to use ohms, whatever you're checking must be off and isolated. In other words, unplugged. Is this plugged in?
No.
Is it off?
Yes.
Is it isolated? I can use ohms. Since this uses a small amount of energy to record it, to find these answers, and I was to have it set on ohms and plug it into this wall outlet, you think that'd be a good solution?
No.
It's going to fry this meter. You don't want to do that. They put a fuse inside so it doesn't blow up and catch you on fire, but it'll definitely damage your meter. So if I want to check voltage, I got to turn it down here to V for voltage.
Hey, Ty,
Yes, sir.
is it the same for all multimeters or just that one?
Just this one. Oh, actually, for most. 99.99%. Some meters are better about protecting it, but if you have it on ohms and hook it up to voltage, it'll damage it. Sometimes just a fuse, but usually it damages, even if it blows the fuse, it'll make the meter not nearly as accurate. Good question. Let's see, I'm going to put one on one side, one on the other side for volts. Have to hold it in, I think. All right, so it tells me that the voltage of this plug outlet is 123 volts. 123 volts. 123 volts. So if I was to plug that in, what do you think the speed of electron flow would be?
8.0392156683.
So 123 divided by 15.3 is what?
Oh wait, I think I got it.
8.0.
8 amps. 8 amps. So let's take my little toaster over here. And here's what's cool about this. When I check amps, I clamp the meter around one of these wires. I don't have to actually touch the wire. How cool is that? So I can split my wires here. I'm going to put it around only one side, like so. I'm going to plug this in. We'll set it down first. Then we'll plug it in. Somebody took all the casing off the side. I don't know why. It's crazy. You guys believe somebody would do that?
I don't know, man. And this class, anything's possible.
They got tired of making toast.
I don't know if they're anything like those AC units out there with the whole thing taken apart. Man, you guys notice on all those AC units, all the screws are taken out?
Yeah, that irritates me very much.
Insane.
All right, so I got 7.3 amps. Now one of the reasons it's off is now that I have a flow going, my voltage will actually drop a little bit. So it throws the math off a little bit, but notice that we are right there, huh? How cool is that? So amps, notice how amps is just a byproduct of those numbers. Isn't that neat? Look at this. All these different things, all of this right here, this is electricity. This is how electricity works.
In a nutshell.
And back in the 1800s, they passed a law about this, and it was called Ohm's law. If somebody asks you, what is Ohm's law? You draw a circle and put E over I and R, and they will know that you know. There's a long formula for it, a whole bunch of words, and all those words equal E over I and R. And it also breaks down to a bunch of formulas. You can say amps, which is speed, electron flow, current, intensity, multiplied by R, resistance, electron flow, ohms, omega symbol, equals E, volts, electrical pressure, potential difference. Or you could also say R, resistance, electron flow, ohms, multiplied by amps, speed, electron flow, current, intensity, equals E, volts, electrical pressure, potential difference. Or you could say E, volts, electrical pressure, push force, potential difference, divided by I, amps, speed, electron flow, current, intensity, equals R, resistance, electron flow, ohms, omega symbol. Or you could say E, volts, electrical pressure, push force, potential difference, divided by R, resistance, electron flow, ohms, omega symbol, equals I, amps, speed, electron flow, current, intensity. But by doing this one thing right here, if I want to know the amps, I cover up I. E divided by R equals I. If I want to know R, I cover up R. E divided by I equals R. Cool, huh?
Yeah.
How awesome is that? That's Ohm's law. Somebody says, what's the simplest possible way you can describe electricity? E over I and R.
They put that on the test, man.
That's on almost every HVAC with any electrical questions is Ohm's law.
So why is everything measured in watts?
We're going to get there. Watts refers to this also.
What you saying? If you say the answer for electricity, you put ER.
I just need to know any two of these, and I can always find the third. As far as how it works, in reality, amps is a byproduct of volts and resistance to electron flow. Make sense? You understand electricity now?
Yeah.
All right, let's move on to advanced electricity. No, first I want to make sure you guys get this, so I'm going to make a little pause here.